Hello, my name is Oskar and I represent the paper Eliminating Abstraction Overhead of Java Stream Pipelines Using Ahead-of-Time Program Optimization, which is joint work with Anders. Java version 8, which was released in 2014, introduced two features from the functional programming paradigm: anonymous functions, also called lambdas, and the Stream API for declarative MapReduce style data processing. To see how these features are used together, we look at the following example. The sum of even squares method loops over an array of integers, filters out the odd numbers, and computes the sum of the square of each remaining number. It's written in traditional imperative style with a loop. If we utilize Java's new functional style features, it might look like this. A stream is created from the input array, then a filtering intermediate operation is applied. This operation is parameterized by a predicate, which in our case restricts the stream to only contain even numbers. The mapping operation is then applied, which squares the numbers in the stream, and finally the sum terminal operation is applied, which computes the sum of the numbers in the stream. The advantages of functional programming are well known. Most importantly, once familiar with this paradigm, the declarative style and absence of side effects tend to make code easier to read and write than the imperative alternatives. However, this increased level of abstraction comes with a performance cost, the abstraction overhead. This graph shows the performance of a couple of Java micro benchmarks from previous work. The blue bars represent the micro benchmark implemented in imperative style, while the orange bars represent functional style with streams. For the method we looked at before, the abstraction overhead of streams is not substantial, but for other benchmarks, streams perform an order of magnitude worse, such as the megamorphic maps benchmarks. In a 2017 study on the adoption of lambdas and streams in Java projects, a developer from the Cassandra project said the following: "Unfortunately, we quickly realized that streams and lambdas were pretty bad from a performance point of view. Due to this fact, we stopped using them in the hot path." Interestingly, this still holds today, 6 years after the release of Java 8. The question is now, how do we get rid of the abstraction overhead? Traditionally, just-in-time optimizations are used to ensure good performance in Java. We argue that the time has come to also pursue ahead-of-time optimizations that can complement the JIT. As shown earlier, the default JIT configuration does not get the job done. However, tuning the JIT configuration can have negative effects for other parts of the program. And in our experiments, manually tuning the JIT parameters does not yield the desired performance. Also, time is cheaper ahead of time, so we can afford more complex analyses to drive optimizations. And JIT optimizations are known to be unpredictable. With ahead-of-time optimizations, we can let the developer know if an optimization is applied. The key optimization we'll use is the following. When the client of the stream library is known, the behavior of the stream library can be statically determined and can therefore be specialized for the client. We propose the Streamliner approach. The Streamliner name is influenced by the key optimization, which is inlining. The structure of the approach is shown here. The input program is fed to the first phase, which finds stream pipelines in the program to optimize. Types are also inferred for stream sources, such as Java connections, if needed. In the second phase, a precise pointer analysis is performed for each stream pipeline. The pointer analysis produces a set of abstract states that are used for aggressive inlining and stack allocation transformations in the third phase. And in the fourth and final phase, a cleanup of the bytecode is performed. Let's now look into the phases in detail. The first phase takes a Java program as input and must find stream pipelines in it to optimize. This is done using the type information available in the Java bytecode of the compiled program. Here we identify the calls to stream, map, and any match as being part of the stream pipeline, marked in gray. Later phases need type information for stream sources, like list in this example. This can be computed by an off-the-shelf analysis such as Møller or suit. The second phase contains the main analysis. is designed to be very precise and therefore uses call site context sensitivity with unbounded call strings. This is of course impractical for programs in general, but it can efficiently analyze small parts of a program, such as the stream pipelines detected earlier. The analysis primarily computes must points to information, which is depicted by the following letters. The use of must points to information allows the analysis to perform strong updates, which leads to a precise analysis result. Here, L1 to Ln represent allocation sites related to the stream pipeline encountered by the analysis, and unrelated denotes other allocation sites. Let's look at the following example method, which contains part of a stream pipeline to see what kind of information the analysis computes. For each program point, the analysis computes an abstract state. This state contains an abstract value for each variable. Here, persons and P have the unrelated pointer value. Since the call to add is not part of the stream pipeline, it's not analyzed. The call to persons stream is relevant. The call is analyzed precisely, and in the process, two allocation sites are discovered, L1 for the return stream object and L2 for the stream splitterator. These allocation sites map to objects in the abstract heap shown in the bottom. The call to filter is also analyzed precisely. A new allocation site, L3, is discovered and added to the abstract heap. The object representing the filtering operation contains a pointer to the previous stream object, L1. The objects form a chain in the heap that the abstract states capture precisely. We will now take a look at how the analysis results computed earlier are used for code transformations. To keep things simple, we'll look at how the call to stream will be transformed. We assume that the pre-analysis computed the type of persons to be array list. With this information, it's possible to resolve the call to stream and therefore inline it. Here the code is shown after aggressive inlining. We see that the call to stream ends up allocating two objects, the splitterator at the top and the object representing the stream at the bottom. As an example, we'll now look into how the stack allocation transformation affects the first object. Remember that in Java, object construction is a two-step process. What goes on in Java bytecode is more closely resembled by the following code. Here, an object is first allocated, and then the constructor is called on the uninitialized object. Let us name the allocation site L2. We begin stack allocation by removing the heap allocation and allocate local variables for the object's fields. The splitterator object has 4 fields: list, index, fence, and expected mod count. These fields are associated with the allocation site L2. The object's constructor must now also be inlined, as the object reference is gone. The constructor simply assigns the parameter values to its fields, but which object does this refer to? In the abstract state computed by the analysis, we know this must point to the object allocated at L2. Therefore, we can transform these field rights into local variable rights. A similar transformation must be carried out for all field accesses to the object allocated at L2. The analysis results from the previous phase can determine if this transformation is possible. Notice that the first assignments to the fields list, index, fence, and expected mod count are now redundant. The next phase will clean up these redundancies. So we reach the fourth and final phase, which is cleanup. The transformations performed by the previous phase introduce a lot of redundant code. We take a look at the example from the beginning, the sum of even squares method. When this method has been transformed, it contains about 2,000 Java bytecode instructions, most of which are redundant. The purpose of the cleanup phase is to remove redundant instructions, making the resulting method smaller and more efficient. This is achieved by applying a variety of intra-procedural analyses and optimizations, such as a must-alias analysis, strongly live variables analysis, and general p-pool optimizations. These techniques are able to drastically reduce code size and the number of local variables used in the method. We can take a look at what the decompiled sum of even squares method looks like after optimization and cleanup. we see that the state variable carries the sum of the pipeline, and the filtering and mapping operations are visible inside the loop. We can compare it to the handwritten imperative style implementation. Although not identical, the implementations are very similar. They even have the same performance, as we'll see next. To test whether our approach can remove the abstraction overhead of using streams, we evaluate the performance of a suite of micro benchmarks before and after optimizations. I'll first explain the legend. So, the blue baseline group corresponds to imperative style implementations written with loops. The orange stream group corresponds to implementations with Java streams, and the green and red groups correspond to implementations written with 2 toy stream libraries. Details about these are in the paper. Also, the dashed groups correspond to implementations that have been optimized with our approach. The y-axis shows the average time in milliseconds for the benchmark to complete, where a lower result is better. The results show that when optimized with our technique, code implemented with streams generally has performance equivalent to that of imperative-style loops. For only one benchmark in the stream group, flat map take, the main analysis aborts, and therefore optimization cannot take place. Testing whether the technique is able to optimize micro benchmarks does not guarantee that it works for stream pipelines in general programs. The aim of the second research question is to answer whether the technique is able to optimize such stream pipelines. To do this, we sampled 28 Java projects from the repos dataset and attempted to optimize detected pipelines in these. The results show that the technique works for 77% of detected pipelines. This is a good result, but getting it to work for the remaining 23% is an opportunity for future work. The conditions for optimization failure are described in detail in the paper. To conclude, streams offer functional style data processing at a cost. Existing just-in-time optimizations cannot fully reduce this cost. The Streamliner approach offers ahead-of-time optimizations that can complement existing just-in-time optimizations. These optimizations are possible due to a high-precision analysis that works with stream pipelines, as these are relatively small pieces of code. Streamliner gives equivalent performance to imperative-style code for 10 out of 11 microbenchmarks with streams. And it works for 77% of pipelines we found in the wild. Covering the remaining pipelines is an opportunity for future work. As part of the evaluation of our approach, we developed a prototype implementation of it. It's made with Java and builds upon the ASM framework for Java bytecode transformation and analysis. Both the implementation and the benchmarks used in the paper are available at the page shown in the bottom. Thank you for watching my talk.